Okay, problem 25, the last one. A sample of 153 university students who recently moved off campus were polled to see whether they agree that off-campus living is preferable to on-campus living. In addition, each was asked how many people live in their current off-campus residence. The results are summarized in the following contingency table. So these contingency tables, chi-square, perform a test for independence, a chi-square test for independence, using alpha equals 0.05 level of significance, our favorite one. What do you conclude? So we're doing a test for independence. Let's go to the formula sheet and look at the components of that. Okay, so chapter 11, chi-square test for independence. Here's what chi-squared is. And then our degrees of freedom, rows minus 1 times columns minus 1. Okay. So I'll write over here chi-squared equals the sum of the observed minus the expected squared divided by the expected, and degrees of freedom, rows minus 1 times columns minus 1. There was a question about degrees of freedom for contingency tables before. So we know right off the bat, 3 rows, 3 columns. So 3 minus 1 times 3 minus 1, that's 2 times 2. So 4 degrees of freedom. So we can get our critical value pretty simply with alpha degrees of freedom. But, okay. So with these contingency tables, there's a good bit that we have to do to get to the point where we're doing this test. Now, we can do this in the calculator in 10 seconds. I'm going to show that at the end. The method that I'm going to show now is using this formula and using the calculator intelligently to help us. Okay. So before we do the test for let's start with the null and alternative hypotheses. Step 1. Null hypotheses, alternative hypotheses. So in a test for independence, the null hypothesis will be independence, that these two variables have nothing to do with each other. They're absolutely independent from each other. So what are we talking about? Their preference on-campus living versus their how many people live in their residence. So number of people in residence, independent, kind of writing small, of campus living preference. That's the null hypothesis. The alternative hypothesis is that they're dependent. The number of people in residence is dependent on campus living preference. I don't know if this color is hard to see, so I'm going to go back to black. Okay. That's our null and alternative hypotheses. Yes. And there's our claim. Okay, step 2. Let's get the critical value. So alpha is 0.05, degrees of freedom 4. Let's take a look. Going all the way down to chi-square. 4 degrees of freedom, alpha is 0.05. 4 degrees of freedom, there we are, 9.488. Critical value is 9.488. And if I draw my little picture here, Remember the chi-square is right skewed, and it's a right tail test. So that critical value is 9.488. Here's my rejection region. Here's my non-rejection region. Beautiful. Now the third step is where it gets interesting, right? What we have here is their responses to the survey or the poll or what have you. Those are our observed values. Each of these values are our observed values. Now we have to calculate these expected values. E, we call them. E, the expected values. And to calculate that, we use the row total times the column total divided by the grand total. And we have to do that for each entry on this 3x3 contingency table. Okay, 3 rows, 3 columns. So, first thing we need to do, find the sums of each of these columns. So, 38 plus 2 is 40, plus 4 is 44. 40 plus 9 is 49. This is 45 plus 15 is 60. Okay. Going across, 6 and 15 is 21. Right? And 9 and 12 is 21. Okay, what's this? This is 38 and 33. That's 71. 71 and 40. 71 and 40 is 111. I think. Yeah, sounds about right. I'll know I'm right if I add these and add these, I get the same. So here we go. We've got, let me put that in red or something. 3, 5, 1, 153. Let's see. 60 and 50 is, what's that? I know I have to subtract 1. 60 and 50 is 110. 110 and 44 is 154, minus 1 is 153. Okay, perfect. Perfect, perfect, perfect. Okay, so now let's find our expected values, right? And I'm going to do this for each position. I'm going to write it here and then I'm going to erase it just to save room and keep this thing nice and neat. You can write it and keep it there, whatever you like. Okay, so for this position here, that's the observed value, right? Well, first let's find the expected value. Sorry. So the expected value for this position is going to be the row total, 111, times the column total, times 44, divided by the grand total, divided by 153. You know what? I think I'll do them. I'll keep them. Because I want you to see them, but I'm trying to be conscious of space here. So let's do it. I'll do it in this little region here. I'll do it in this little region here. And I'll use my colors. I'll use blue for this one. I'll use green for this one. And I'll use purple for this one. For that column. So first column, first entry. So I've got 111 times 44 divided by 153. For the second entry, I've got 21 times the row total, 21, times the column total, 44, divided by the grand total, 153. This position, row total, 21, column total, 44, over the grand total, 153. These two will actually be the same, so that's a good thing. So let's use the calculator. Let's determine those. So I've got 111 times 44 divided by 153. 31.9. I'm going to use 3 places. I'll use 2 places. 31.92. Next to 21 times 44 divided by 153. 6.04 for both of these. And what I'm going to do, space is so tight here. What I'm going to do is I'm going to, in parentheses, write the expected value, 31.92, and here's 6.04, here's 6.04. All right, the expected value is right next to the, write the expected values right next to the observed values so we can see them. You'll be able to do this a lot more clearly because you'll have more space. Now I'm in green. So now for this position, row total is 111 times the column total is 49 over 153. Next position, 21 times 49 over 153, and 21 times 49 over 153. There's slicker ways you can do these calculations, but I'll keep it simple. 35.55. That's the next one, 21 times 49. 6.73, rounding, 6.73. So here, let's say 35.55, 6.73, 6.73. Okay, you can match those up that way. And then for the last column, I have 111 times 60 divided by 153, 21 times 60 divided by 153, and the same for the last. This is just us finding the expected values. This is observed value minus expected value divided by the expected value. And this expected value is the case of if the people in the residence were independent of, the number of people in residence were independent of campus living preference. These are the values that we would expect to get if that was true. 111 times 60 divided by 153, 43.53. Oh, dropped my pen. 21 times 60 divided by, whoops, 21 times 60 divided by 153, 8.24. And you notice that these values are comparable to the ones we have, right? 43.53, 8.24, 8.24. A little hard to see, but since I have them here, that's a good thing. Okay. Cool. Great. So now we have our observed values, we have our expected values. Now I can find, here we go. Now I can find chi-squared. So I'll show you what we would do if we didn't have a calculator, and I'll show you what we'll do because we have a calculator. So this is step 3. We're trying to find chi-squared. Step 3. So chi-squared is the sum of the observed values minus the expected values squared divided by the expected values. So here's how I would do this. Observed value minus the expected value. So I would have to do 38 minus 31.92 squared divided by the expected value, 31.92. Plus the next one, I'll go over this way. 40 is the observed value minus the expected value, 35.55 squared over the expected value, 35.55. Plus the next one. I'll have to do this 9 times, right? 33 observed value minus the expected value. So, sorry, it's 43. 43.53 squared over 43.53. Next position, 2 minus the expected value 6.04 squared over 6.04, and so on and so forth. I would have to do this 9 times, right? 1, 2, 3, 4. I've got the first 4, then 5, 6, 7, 8, 9, all to find chi-squared. You can do it that way, and if you're careful with your calculations, you'll get your answer, right? But I'm going to be a little slicker than that. Okay, so here's what I'm going to do. And again, I'm going to show a all calculator method at the end. Okay, but so here's what I'm going to do. I'm going to go to stat. Well, let me clear my values for a second. Mem 4, clear all this, enter. Okay, I'm going to go to stat, edit. In my L1 column, I'm going to enter the observed values. I'll be systematic about how I put them in. 38, going across 40, 33, 2, 7, 12, 4, 2, 15. L2, I'm putting the expected values. I'll use my bigger stuff here. So 31.92, going across 35.55, 43.53. Just make sure they match up. 6.04, 6.73, 8.24, 6.04, 6.73, 8.24. Okay, so I have my observed values in L1, my expected values in L2. I'm going to exit out of here. Now here's what I'm going to do. Here's the nice part about this. I know my formula says chi-squared is the sum of the observed minus expected squared over the expected. Now, so the way that I'm going to do this is I'm going to use the sum formula. And my observed are in L1. My expecteds are in L2. Let me fix this. Squared over L2. That's the formula I'm inputting into this calculator. And it'll output chi-squared for me. Here's how I do it. I have to go to the list function, the list feature here, to get that sum function. So second in stat for the list, go over to math, and then option 5 is sum. List, second list, go over to math, sum is 5. In parentheses, my numerator, L1 is right here, L2 is right there. See them in yellow? Second L1 minus second L2, close parentheses squared, divided by L2. I hit enter. There's my sum. That's my chi-squared. That's what I would have gotten if I did this process with 9 different fractions, rational expressions to add. So let's say chi-squared is 18.25. Chi-squared is 18.25. Okay? And this is our test value, our chi-squared test value. So when I check here, 18.25 is definitely in that rejection region. It's greater than 9.488. So we need to reject the null hypothesis and the statement that we make. Reject the null hypothesis, and our statement is, if I'm rejecting this null hypothesis, then there is enough evidence to support the claim that these are dependent, right? That the number of people, etc., is dependent on campus living preference. The number of people in the residence, I'll write it. Okay, so this was the way, using the formula mixed with the calculator, having to do all of this here. It's a long process. Do I necessarily want you doing this long process on exams? I don't know. I think the calculator approach is much shorter. It's much quicker. It's much, you'll see. I'll show it to you. just the calculator approach by itself. Okay, I'll show it to you. Here we go. Give me one second. Okay, so in order to do this, in order to use the calculator exclusively, we have to create a matrix. And that matrix will be the original contingency table, right? The original contingency table, we're going to create that matrix. If you see, you might see the word matrix right underneath there. Well, that really says matrix, M-A-T-R-X, above the x to the -1. So second that, we're going to create a matrix. So let's edit one of the ones that we already have. I always like to edit A. I'll edit that one, right? I'll edit that first one. And you have to tell the calculator what's the size of the matrix, how many rows by how many columns. So this is 3 rows, 3 columns. So you're telling it 3 by 3. Make a 3 by 3 matrix. I'll fill in the values, right? So let's fill in the values. 38. It goes across horizontally. 40, 33, 2, 7, 12, 4, 2, 15. Okay. So that's our matrix. We input that. And that's really all we have to do, right? Because now that that matrix is there, now I can go to stat because I'm doing a hypothesis test. Go over to tests. And I know that I'm doing a chi-square test. This is a chi-square test for independence. That's chi-squared. That's chi right there. Chi-square test for independence. So I click enter. My observed values are in A. That's matrix A. That's where I put them. The expected values, we didn't put them in, but they'll be there. Calculate. And as you see, we get our chi-squared of 18.25 or 26 or what have you. And what we also get is this p-value, which is nice to use because, I mean, the p-value method works really well here, and it's just one step. Because remember, the p-value method says, if the p-value is less than or equal to alpha, reject the null hypothesis. If the p-value is greater than alpha, do not reject the null hypothesis. So in this case, right, our alpha level was 0.05. Our p-value is 0.001. Do you see that? So our p-value is 0.001. Our alpha is 0.05. Comparing the same position, p-value is definitely less than alpha. So reject the null hypothesis is the claim. Now realize all I did was input the matrix, go over to chi-square test, and I have that information. And I can use that information to do what I need to. It also gives you degrees of freedom. If you want to find the critical value, you can do it right there. Find this critical value and then compare chi-squared to that critical value. It's a quick approach. It's quick and dirty. Now look at what else. If I go back to the matrix, right? You see how now there's a 3 by 3 matrix in B? That matrix is actually, wait, hold on. Let me go back into the matrix. Let's go to edit it and see what it looks like. Look at that. That matrix B, look what it calculated the expected values for us. Look, 3.9, 31.92, 6.04, 6.04, 35.55, 6.73, 6.73, 43.53. 8.2, it did those calculations for us. So once you put in that matrix in A, the calculator would automatically in B give you the expected matrix, the expected value matrix. Okay? So, and that's how you do this. Now if you want to clear out those values, clear out those matrices so there's nothing in there, you go to second memory, go to memory management, go to matrix because I want to clear out the matrix, and then just hit delete on each of those. Delete, delete. And then when you go back into matrix, they'll be empty, there'll be nothing in there, and you can start fresh. So that's 2 ways to do this. Well, 3 ways really if you do all the calculations yourself. There you go.